Hello, George Notchik here. Here's a dynamics problem that we're going to solve that's a little more difficult than the previous problems. What we have are two buildings. We have building A here and building B. We have a projectile launcher that's back away from the edge of building A, and we have a target that we're going to try to hit that's back away from the left edge of building B. The distance that the launcher is from the right edge of building A is 3 meters. Here's our coordinate system that we're setting up. Is in the x direction. Our coordinate system starts here. This is the x equals 0 at time equals 0 when the projectile is launched. And the edge of the building is at x1. That's 3 meters. Building x2, the left edge of building B here from the right edge of building A is the distance x2 minus x1, which is 120 meters. Building A is 50 meters high. Building B is 70 meters high. So the height difference is little hb, which is 70 minus 50, or 20 meters. Now, the distance that the target is from the launch point is x of f, and that will be when the projectile hits it at time tf. This is final time, the x distance final. Well, the final time will be the distance that the target is from the left edge of building B, and that is given as 5 meters. That is, xf minus x2 is this distance, which is 5 meters. And we know that the distance from the right edge of building B to the left edge, or the right edge of building A to the left edge of building B, is x2 minus x1, or 120 meters. So the final distance will be, solving for xf, it'll be 5 meters plus x2, but x2 minus x1 is 120, so x2 is 120 meters plus x1, and we're given that x1 is 3 meters, so then xf will be 5 meters plus 120 plus 3, or 128 meters from the launch point to where the target is. Now, the problem is find the initial velocity that we need to launch the projectile at if the projectile is being shot at an angle theta with respect to the horizontal of 38 degrees. So we want to know what the initial velocity needs to be in order for the projectile to be lobbed up and hit the target here on the roof of building B if the angle of launch is 38 degrees. And we're going to neglect the air resistance in this particular problem. So, the projectile will reach a height yp with respect to my y-axis. I'm setting up the y-axis as the height of building A. What only matters here really is not the absolute heights of the buildings, but the height differential. So we'll set y equals to 0 at the height of the lower building, and then our height with respect to the height of building A will be yp. That will be the maximum height of the projectile, and that will occur at time tp, and the x distance along at the peak will be xp. So here's our coordinate system. We have the launch point at time equals 0 at x equals 0. The right edge of building A is at x1. The maximum height of the projectile is at xp. It occurs at time tp. And the left edge of building B is at x2, and the target is at a distance xf from the launch point, and the projectile will hit that target at time t final, or tf. So this is the problem that we need to solve. We need to solve for v0. So now we'll go ahead and do that. Now, to get started, we first observe that only the difference in the building heights matters, not the absolute heights of the buildings. So the difference in heights is our small h of b, which we determined to be 20 meters. That is the height difference between building B from building A, or 70 minus 50. Secondly, we need to note that there isn't any way we're going to hit the target if the angle is too small to clear the edge of the building. And that I'm showing here. Here is the building B, and if we're on building A, the roof of building A here, that's this y equals 0 line along here. If theta 1 is not large enough so that if we had, say, an infinite velocity on this projectile where we're going to just shoot and hit the edge of this building, that if theta 1 isn't large enough, then we're never going to hit our projectile or our target here with the projectile. So what's this angle need to be? We first need to check that out. Well, the height of the building is 20 meters, and we know that the distance from the launch point to the target, or to the edge of the building, is x2. Well, x2 minus x1, the distance between the two building walls, is 120 meters, and x1 is 3 meters back, so the distance from the launch point to the edge of the building that we need to clear the corner is 123 meters. So this angle theta 1 then is 20 divided by 123. That is the tangent. So theta 1 would be the arctangent of 20 over 123, or 9.24 degrees. So choosing an angle theta of 38 degrees, we are guaranteed will clear the edge of that building. So the next question then is how fast does that projectile need to be in order to get lobbed up and then come back down to hit the target? And this is our angle 38 degrees. So what we're going to solve for now is this initial velocity, v0, so that when it's launched at 38 degrees, is going to hit our target at the top of building B. Okay, now, so first let's look at, get some equations here. Once the projectile hits the peak, we need to find an expression for the y value, or the vertical value of the projectile height, as a function of time. And we will write that as y of t. Now again, this is for t greater than or equal to the time that we reach the peak. So for t greater than tp, y will be the peak value, yp, minus 1/2 the acceleration due to gravity, times t minus t peak squared. That is our equation. We had this from our last video on ballistic flight. That is, if given, we know that acceleration is the time derivative of velocity with time, or the second derivative of y with respect to time. Since velocity is just the first derivative of y with respect to time, we're taking the derivative of that. So the acceleration is the second derivative of y with respect to time. Well, what's the acceleration? The acceleration is minus g. That is the acceleration due to gravity. So if we integrate this once, we get y, the derivative of y with respect to time is minus gt plus some constant, which would be the initial velocity, call it v0. And then we integrate again, y equals, integrating minus gt with respect to t, we get minus gt squared over 2 plus v0t plus an initial position, y0. Well, what is y0? Well, at y0, remember we're starting at the peak, so y0 is y peak in this case. And then what's the initial velocity? Well, the initial velocity, once the projectile hits the peak, the vertical velocity is 0. So this goes to 0. So we're starting with t equals 0 at t peak. So when putting in terms of time from the initial time we start, we are going to write this as minus g, which is t minus t peak squared plus y peak. And that's the equation we have here. It's y peak minus g over 2 t minus t peak, because this is actually starting, we'll call it t prime. That's starting with time equal to 0 at the peak, and we got to convert that t prime is just t minus t peak in transforming from the prime system to the unprimed system. So just to show you where that equation came from. We now have our equation that describes the vertical height of the projectile as a function of time after it has reached its peak. That is, this equation is greater for times greater than t peak. Now we need to get a relationship that relates the time the projectile takes to get to its peak to the actual peak height, y peak. And the way we do that is we need to solve for y peak in terms of t peak. Now, in this part of the flight of the projectile, that is from t equals 0 to t peak, during this part of the flight when the projectile is moving upward towards its peak, we know that y as a function of time will be the initial velocity in the y direction times time minus the acceleration due to gravity divided by 2 t squared plus the initial position in the y direction. And again, we get this by doing a double integration on the acceleration due to gravity. Now, at y equals t peak, what's the y value? Well, the y value is y peak, and that is equal to the initial velocity in the y direction times t peak minus g over 2 t peak squared plus y0. Well, we established our coordinate system, so the projectile is at y equals 0. So the initial position is 0, so we don't have that part of the term. Now, y peak then is equal to this. Okay, that's our equation for y peak. Now, let's look at the velocity as a function of time. Well, the velocity in the y direction as a function of time will be the initial velocity in the y direction less the acceleration due to gravity times time. Now, to reach the peak, the velocity of y at the peak is 0. Remember, the projectile comes up, and it hits its peak. Well, there's no longer any vertical velocity or in the y direction when it hits the peak. So that is 0, and that is equal to the initial velocity in the y direction minus gt peak. So we have that equation. So solve for t peak. T peak then is v0y divided by g. Okay. That's from this equation here. Well, we got v0y in terms of t peak that we can put in this equation here. So we have y peak is equal to v0y times t peak. We'll solve for v0y in this equation. v0y equals gt peak. So we put that in for here. So we have y peak equals v0y, which is gt peak multiplied by t peak, so that's squared, minus g over 2 t peak squared. So we can factor out our t peak squared, and this is g minus g over 2, or g over 2 t peak squared. That's our y peak. Now, in terms of t peak squared, so when we're shooting a projectile, the relationship between the time it takes to reach the peak and the peak height is this equation. So we can now put that in to our equation here to get a relationship. See, we have y peak now in terms of t peak. We can put into this equation. This is for after it's reached the peak, and now we can get a relationship for the height of the projectile as a function of time. So we'll get this substituted in and work on that equation. Now we have a relationship between the peak vertical height and the time that it takes to reach that peak vertical height. That is, the vertical height at the peak is related to the time to get there from the initial shot of the projectile by y peak is g over 2 times t peak squared. And remember, this equation is for times once the projectile has reached its peak, for t greater than or equal to t peak. Now, what we're going to do is solve this equation for the time that it takes for the projectile to reach its final position. That is, when it hits its target. Well, when it hits its target, at the final time, the height of the projectile will be small h of b. So, y at the final time, tf, is h of b, and that is equal to y peak minus g over 2, the final time, t final minus t peak, that quantity squared. Well, solving, we have hb equals, now we put in for y peak this equation here. Y peak then is g over 2 t peak squared, and then we minus g over 2 t final minus t peak squared. Now to simplify this, I'm going to multiply through by 2 over g, since we have that same constant factor on both terms here. So twice over g hb is equal to t peak squared minus the quantity t final minus t peak squared. We expand this out, so we've got t peak squared minus, well, expanding this out, t final squared, so we have a minus t final squared, and then we have minus twice the cross product here. with a minus sign, so it's plus twice T final, T peak, that's it, twice T final, T peak, and then a minus squared, minus T peak squared is a plus, and so we subtract that off, so we have minus T peak squared. Now notice our T peak squareds cancel, and we end up with twice T final, T peak minus T final squared. Now, let's write this out. This is equal to this. So let's put everything out on the left-hand side. So we have T final squared minus twice T final, T peak, plus 2 over G HB is equal to 0. With our quadratic equation in the final time with respect to the time to get to the peak and the height that the projectile needs to reach, this doesn't quite give us everything we want because we don't know really what T peak is yet or what Y peak is. We just have relationships between them. Now, in order to get a useful relationship, remember, we're solving for the initial velocity. Well, we just derived here a bit ago, there is a relationship that we have that the initial velocity in the Y direction of the projectile is equal to G times the time that it gets to the peak of its trajectory. Well, VOY is the initial velocity times the sine of the angle at which the projectile is shot at. But we don't know what V0 is, so we really don't know what T peak is. We know T peak in terms of V0, so in order to get a solution, we now have to look at the horizontal component. Now, remember that the horizontal component in any ballistic flight, there's no forces acting in the horizontal direction, so the projectile velocity component in the horizontal direction always remains constant throughout its flight. That's a key point. So, the distance in the x direction that the projectile travels is going to be V0, that is the x component of the initial velocity, times the final time. Because, again, the x component of velocity throughout the flight of the projectile remains constant, so the distance it travels in the horizontal direction will just be that component of velocity times the flight time, or the final time of the flight. Well, remember V0x is the initial velocity times the cosine of theta, and that's times the final time. Now, let's solve for TF. TF will be XF, which we know, divided by V0 times the cosine of theta. Well, we know XF, we know theta, and we're ultimately going to be solving for V0. Now, we'll put this into this equation here. What we're going to do here now, again, is make some substitutions. Here's our equation. I'm putting in for T final, the final time, which is XF over V0 cosine theta. So, we have XF over V0 cosine theta squared, that's our TF squared, minus twice the TF, which is XF over V0 cosine theta. And then for peak, T peak, remember we have this equation here, V0y is equal to g over t peak. Well, V0y is the total initial velocity that we're shooting the projectile out times sine theta. So if we solve for the time to the peak, t peak then is V0 sine theta divided by g. So we put that in for t peak here. That's this quantity here. And then we have plus 2 over g hb is equal to 0. I'm going to multiply through now by V0 cosine theta squared. So we end up with an xf squared minus, then we have V0 squared cosine theta squared so when we put this in here, one of the V0 cosine theta squareds cancel with this, and we end up with a V0 sine theta times V0 cosine theta with a 2. So make use of a trig identity. Twice sine theta cosine theta is sine 2 theta. So what we've done here is we're multiplying by V0 squared cosine squared theta. One of these cancels with that, and we end up with V0 squared. We have V0 times V0. So that's V0 squared, xf, and then we have twice sine theta cosine theta, which is sine 2 theta, and then divided by g. And then we have 2 over g hb times V0 squared cosine squared theta. Now, I'm going to multiply this now through by g. So we'll get rid of the g here, we'll get rid of the g there, and we have g there, and then 2 sitting there. Now, we can factor out what I'm going to do here is move these two terms to the right hand side. So we have g xf squared is equal to xf V0 squared sine 2 theta minus 2 hb V0 squared cosine squared theta. We don't need this stuff here, so we'll get rid of this. All right, now let's look at what we have here. Let's factor out a V0 squared. So we have V0 squared times xf sine 2 theta minus 2 hb cosine squared theta. Now, what we're looking for, remember, is V0. So, solving for V0 squared, this is equal to g xf squared divided by xf sine 2 theta minus 2 hb cosine squared theta. So now we have an expression for V0, the initial velocity that we need to shoot the projectile at, in terms of known quantities. That is, we know the distance from the launcher to the target, xf, in the horizontal direction. We know the acceleration due to gravity, and we know the angle at which we're shooting the projectile at, and we know the height difference between the two buildings, hb. So we've now solved for our projectile velocity that we need. However, this is a quadratic. So we need to find restrictions on V0 so that the denominator doesn't go to 0. See, we have a difference here, and this will blow up if the denominator goes to 0. So we're going to need to determine restrictions so that we don't end up with an indeterminate velocity, or that it's going to blow up or become negative. Remember, we're going to be taking a square root to get V0, so we can't have this quantity either go to 0 or become negative to take the square root. We can't take the square root of a negative number and end up with a real velocity. So let's examine this a little further now. When does the denominator vanish? When does the denominator become 0? Well, this becomes 0 when the term here, x f sine 2 theta, is equal to 2hb cosine squared theta. That's when the denominator goes to 0. Well, let's expand this out. Sine 2 theta is twice sine theta cosine theta, then xf equals 2hb cosine squared theta. Well, the 2's cancel, and we can cancel out one of the cosines. So we end up with sine theta xf equals hb cosine theta. So we can write this. Let's divide through by cosine theta. And that cosine theta goes out, so we have the tangent of theta is related to xf and b. So we can write this as tangent theta equals hb over xf. Now we know hb and we know xf. This corresponds to an angle theta 1 that's going to go like this, right through the building. Because remember, HB is this height, and XF is this distance. So the tangent of theta, or the angle theta, let's call it theta 1, is going to be that angle such that its tangent is HB over XF, and that's the building height, and then divided by the distance over to the target. And to do that, we'd have to shoot through the building. So the denominator will go to 0 and the velocity blows up in an impossible situation. We're not going to be shooting through the building. So that's one of the restrictions that we're going to have. The minimum, remember, allowable angle that we already determined was when we were going to hit the edge of the building. So theta, this theta, let's call it theta 2, because we already solved for theta 1. Theta 1 is 9.24 degrees, so theta 2 is going to be less than theta 1. Theta 2 is less than theta 1, so we know that's not going to be a solution. So for there to be a solution, a launch solution, our angle theta has to be greater than theta 1 and greater than theta 2. And we've already determined that that's the case for the example. So now we have our solution here. So let's put in some examples and see where we're at with this. I've now put the numbers into the equation. Here's our equation for the velocity squared that we need to shoot the projectile out in order to hit the target on the other building. Remember, we're shooting at an angle of 38 degrees. The height difference between the buildings is 20 meters, and our acceleration due to gravity, this is the standard acceleration due to gravity, 9.80665 meters per second squared. When you put those numbers into this equation, this is what we get for the velocity squared. 1617.08 meters squared per second squared. Take the square root of both sides. So our initial velocity to hit the target has to be 40.2 0.213 meters per second. Now what I've done here is I built a table, and you can use it to check yourself on various parameters using the equations that we've derived. Is I have the initial velocity, 3 different initial velocities. Here's the one that we just solved for, that we need to shoot the projectile at in order to hit the target. Here's something just a little bit less. It's 40 meters per second squared rather than 40.213, and then one a bit higher at 50 meters per second. So we can see what's going to happen here. Our initial velocity in the y direction, let's use the one for hitting the target, is 24.785 meters per second. In the x velocity, 31.688 meters per second. The time that it takes to reach the peak is 2.525 seconds. The peak height is 31.251 meters above the building that we're shooting the projectile from. The time that it takes to hit the target, the final time, is 4.0394 seconds. The distance out, we already know that, but it's 128 meters. The way we get this is multiplying the x component times the flight time. The final time, the product of these two numbers has to come out to the distance to the target. And then the final velocity of the bullet, of the projectile, when it's coming down, what we're looking at, this is the final velocity vector here. I'll call that VF. That is the total velocity when it hits the target. And this is 35 meters per second. Now, and then the distance out from the launch point to where we hit the peak is 80 meters when we actually hit the target. Now if we go a little bit less than the required velocity, we can see we fall short of the target a bit. And we can see that the distance to the target that the projectile makes, the target is out at 128 meters. That's what we solved for here. And we land a little bit short. We're almost 2 meters short of hitting the target when our initial velocity is 40 meters per second. And when we up our velocity 50 meters per second, we overshoot the target by almost 100 meters. So here are the values. You can compare against the equations, and this is the solution, that the required velocity as a function of the angle of launch for the projectile in order to hit a target out at distance xf from the launch point, and where the target is above the launch point by a height hb. I'll zoom now into the numbers so you can see them a little better. So here is a copy of my notes on the solution to this trajectory problem. I didn't put down the equations, and you can see them here in final form that we derived in this video and the previous trajectory video. Under V0 here are the equations that I use for computing all the values. And here are the values that I had up on the board for V0 of 40 meters per second and 50 meters per second. And of course here's our trajectory diagram. As I was mentioning, I'm working on a video on the solution of the twin T network that I posed to the viewers about a year ago to solve. And I will be solving the network completely using different techniques, my flow graph technique, and superposition, node voltage method, and source transformations. And I'm going to be going through the network in considerable detail. It's one of my favorite networks, and I may have to divide the video up into several sections, but I'll try to get it all in one video. But it'll probably be a long video because there's an awful lot of algebra in solving the network in the frequency domain and then analyzing the circuit. We'll be looking at output impedance, we'll be looking at frequency response, and then also the effect of nonlinear components on the behavior of the network. And I'm just going to give you a sneak preview here. I'll show you the network. I actually built up a network that I will compare the theoretical analysis to a practical circuit measured on a precision network analyzer, actually 2 precision network analyzers, and I'll just give you a sneak peek on what I'm working on right now regarding that network. Here's a twin T network that I built up. It has the capability of being either a passive or a bootstrapped active network, depending on jumper settings. And we'll be looking at this in depth in one of my next videos. And here is the response of that particular network on a Hewlett-Packard 3577 network analyzer. The response is going between 100 Hertz and 10 kilohertz. The notch depth, the notch is at about 1500 Hertz. Here's the phase response. You can see that. Back to the magnitude response, and here's a polar response of it. And I also have it analyzed here on a Hewlett-Packard 3563 network analyzer. The trace is stored, the response is stored, and here again you can look and see the phase response here, and both the amplitude and phase response together. Go, and you can see that the frequency of the notch, the marker there, is on the notch, and that's at 1.5849 kilohertz. But we'll be looking at this in depth, comparing both the theoretical to the actual measured network in the video that's coming up. So that's kind of a sneak preview of what I'm working on right now for one of the next videos.